Hi everyone, and welcome to the Omnis Automotive series. My name is Benjamin Leroy, and today I'm introducing a new series of short talk about CFD, or Computational Fluid Dynamics Solutions for the automotive industry. In this series, we will raise typical CFD pain points and how to address them without compromising on what matters most: ease of use, robustness, turnaround time, but also accuracy. And this through practical examples in the automotive industry. Now, in some of the episodes, we will hear it directly from the automotive OEM themselves to see how they handle it. Today, a unique and reliable CFD solution for every need in the automotive industry does not exist, at least not yet. And the simple fact of describing what you have to take into account to model your problem is complex. So let's step back a bit and have an overview here.
Starting from an application standpoint, the range of application is actually quite vast. When you have to deal with a lot of different topics: aerodynamics, aeroacoustics, thermal management, climate control, powertrain, rotating equipment, water management, etc., etc. Each of them further unveils more specific fields, such as front-end airflow, underhood thermal management, critical component cooling like EV batteries or motor, brake discs. This is only to name a few. Now, for each of these applications, you want to use the best possible tool for the job. And this means the best modeling technique. Let's take the example of external aerodynamics. While we're now fairly confident that finite volume is superior to finite element or finite difference methods, today there's still no clear consensus between finite volume and lattice-Boltzmann methods. And there are questions that will guide you for the choice of one particular method. Should you use steady or unsteady modeling? How much can you trust the level of accuracy of your solution compared to real-life physics? Do you need absolute level of precision, or will relative interranking between designs do? Answers to these questions will vary depending on where you are in your development cycle as well. Past these, important considerations, then the classical CFD workflow goes as follows. You have to handle the CAD representation of your car, possibly dirty. You then have to prepare and clean it up, making it ready for simulation, to be able to further discretize that into millions and millions of high-quality cells. You then have to set the right boundary condition on every single component, to be able to finally compute the numerical solution using the tool of choice. And finally, you can analyze the results upon convergence. Sometimes this workflow requires the use of different tools, with various levels of compatibility between these tools. Now, what about software selections? Chances are you're running a mix of tools from various software vendors, from CAD input, to CAD cleaning, to meshing, to solving, and maybe even post-processing. Potentially, there might even be an open source solution in the mix, which is being maintained somehow by another department to virtually get software costs down. And that's even leaving out considerations about hardware, CPU versus GPU, for example, and the pressure from your management notwithstanding, to get a solution as quickly as possible. Although, why compromise if you can get that full workflow in a single seamless environment? Maybe you could even get the most efficient tool for each part of the job in that same workflow. And above all, those tools could come with a flexible licensing scheme, ensuring you're only paying for the time you're using the solution, all the while making an optimal use of the current IT infrastructure. Maybe you're even running directly in the cloud.
Now, back to the external aerodynamics example. The reality has to be simple. You want form to follow function. So you change a part on your car, you just want to know if it improves your baseline design efficiency or not. So it means that for an aerodynamicist, for example, knowing if the device he or she has designed will be effectively reducing the drag and improving the front to rear downforce balance. Or will it be providing these extra valuable kilometers of range for the new electric vehicle project, or save millions of euros in CO2 emissions penalties? And time cannot be wasted, both in conceptual design down to production phase, especially when the time to market of a vehicle from R&D to street is now roughly reduced to a year. Now, what if tomorrow you could get all of this in a single environment where CFD has been the primary focus from the start? Well, in the next few weeks, we will start the Omnis Automotive series, where we'll address each of these pain points from the user point of view. Future of CFD is definitely exciting, so stay tuned for the first episode.